Hello, good evening. So this is, today we have IMSC 60 Distinguished Colloquium by Professor Rob Pisarski. And it's a great pleasure to have him with us. So for the students and everyone here, I just want to tell a few words about him. So Rob did his PhD with Professor David Gross in Princeton, after which he was a postdoc at Fermilab and Yale. And after that, he moved on to Brookhaven National Laboratory, where he is there since 1980, end of 80s. And Rob is one of the pioneers in our field. He has worked in many interesting problems in QCD, mainly in finite temperature densities. He is very well known for his hard thermal loop perturbation theory, which he developed with Eric Bratton. He also worked on this semi-QGP, or the non-perturbative model of the Quark-Gluon Plasma, and also about the quark-ionic matter, among his many other pioneering works. So Rob has seen this field grow over these years, and he will share his insights with us. And for those who already sent papers to Physical Review D, he's also an associate editor of PRD. So many of our papers goes to him for reviewing. And he's also a fellow of the American Physical Society. So today, it's a great pleasure and honor for us that Rob is giving the distinguished lecture to celebrate our 60th foundation year. And I would give over to Rob to please deliver his lecture.
Thank you very much,
Rob, please.
Sayantan. I thank Sayantan and the other organizers for the great honor of the invitation to speak at the Diamond Jubilee. It's certainly very positive to see the flourishing of this institution over the years. What I'd like to talk to you today is about the field in which I work. And I first remind you of two other fields in which we can say they were golden ages. And the fact that there are golden ages is often due to circumstance, to just the confluence of various circumstances. But it's clear when it happens. And in the past few years, there have been two that I'm sure you have heard about. One is based upon the idea of Einstein's theory of gravity, that colliding black holes can produce ripples in space-time, and that this leads to the production of gravitational radiation. And after many years, the LIGO instrument with detectors in the states of Washington and Louisiana, each with an arm 2 kilometers long, where they were looking at interference between, I'll try moving the mouse so I don't, well, I'll leave that, between these two arms. And what's amazing is that when the collision of black holes first occur, when they occur, they're in fact the brightest thing in the universe for a very brief period of time. The first event was measured in 2015 between two black holes whose combined mass was about 70 times the mass of the sun. And 2 times the mass of the sun was emitted in gravity waves. It was about 1 million light years away. And the Nobel Prize was awarded in 2017 to experimentalists Rainer Weiss and Barry Barish, and to theorist Kip Thorne. It was clearly an astonishing experiment, involved about 1,000 physicists, and involved about $1 billion to build and run it. And there are many new experiments going ahead, and this will clearly be a very interesting area in the future. We now have many more candidates, and in fact, we now have radiation from neutron stars, which are typically 1 or 2 solar masses, and much heavier black holes. And the collision of neutron stars will tell us a lot about the equation of state of cold nuclear matter that I'll mention at the end of my talk. And in particular, there was a collision in 2019 between an object that was 23 solar masses and one that's 2.6. And this is very interesting because it's far beyond the mass limits that we expect from neutron matter. Okay, the other experiment is that at the Large Hadron Collider at CERN. This was the discovery of the Higgs boson. This involved about 10,000 physicists and cost about $10 billion to build and run. The physics started happening from 2010. They discovered the Higgs in 2012, and consequently, the Nobel Prize was awarded in 2013 to Peter Higgs and Francois Englert. And the great surprise here is that an expected new symmetry of supersymmetry, there's presently no signs of it. Okay. Okay, I have to apologize. I meant to hide some of my slides, so I'm just going to skip through those. What I'm going to tell you about today is the following. And we all know that there's 3 states of matter: gas, liquid, and solid. There's, in fact, a 4th state of plasma. A plasma is easy to understand. The atoms are composed of electrons with negative charge orbiting positively charged nuclei, such as a proton and a hydrogen. A plasma, you pump energy in, either heat or an electric field, so the charges can move freely and independently. This happens in a fluorescent bulb, which is probably lighting the room you're in. It happens in a flame at 1,000 degrees Kelvin. And it happens in a sun where you get from a temperature at the exterior of, say, 10,000 degrees to 10 million degrees. What I'm going to tell you today is matter that creates 1 trillion degrees. And if nothing else, I want you to take that away, that by the collisions of large nuclei at very high energies, we can make something that's 1 trillion degrees. This is a collision, a cartoon of a collision between 2 heavy nuclei. It's at such high energies. I'll explain the dimensions later, but that it forms a thin pancake because you're going at such high energies that you have Lorentz contraction. And the 2 nuclei collide, and they form typically thousands of particles. And from this event that lasts about a billionth of a second, we can deduce indirectly the properties of the matter that was created. And we believe we created something that's called the Quark-Gluon Plasma, and explain to you later what quarks and gluons are. This involved about 1,000 physicists, cost about $1 billion to run. And the reason why I've been keeping this up is that you can see in all of these experiments, it cost about $1 million per experimentalist. And it's interesting that it's a constant over all of this time, all of these different fields. But the conclusion that I'll draw is that this qualitatively new plasma is something that I and many of us in the field believe is worthy of a Nobel Prize. I'll suggest 2 people who might receive it. It probably won't happen because of the fact that the Nobel Prize is limited to 3 people, and because it's not quite as clear who it was really stood out in the field. But it's clearly a qualitatively new state. Okay, so first of all, I'm going to give you a very brief introduction to gauge theories. This is meant for undergraduates and the like who have never heard of this, and so will perhaps be a bit tedious to more senior researchers, but I think it's important to go over. So we're all familiar with electric charge. Electrons have 1 negative charge, protons have 1 positive charge, and it's just a number. What matters is the sign, but you can add the charges together So in a hydrogen atom, one electron, one proton, the total charge is 0. And they interact according to the usual Coulomb potential. So charges of opposite sign attract and those of like sign repel. And we now understand that the potential we can think of is due to the exchange of photons or light. This was first understood by Michael Faraday and others in the early 1800s, and he really was a very intuitive experimentalist. This is a picture to the right of his laboratory at the Royal Institution, and it's amazing that he was able to deduce such sophisticated phenomenon using such relatively elementary equipment. The equations for electromagnetism were unified by James Clerk Maxwell in the 1860s, and these are the well-known equations that we study as undergraduates and graduate students. But in fact, there's a much more general understanding, and that's the following, that, let me just, yeah. The basic idea is that what's really important is that the charge is just a number. And this is not obvious, but it's now understood that this is related to the fact that there's a hidden phase in electromagnetism, or the couplings of light. And it's like the rotations on a circle. So I could imagine a circle where I just have an angle, theta, that goes from 0 to 2 pi. And the point is, if it's just an angle, then the order of the rotations doesn't matter. I add them together. So if I take theta 1 plus theta 2, it's the same as the converse. This is what's known as an abelian group, developed by a Norwegian mathematician, Niels Abel, in the beginning of the 1800s. And what electromagnetism really is you have this phase, and it can be rotated independently at each point in space-time. And this is what's known as an abelian gauge theory. And this is work that's led to a lot of modern work. In particular, there's a notable prize in mathematics, the Abel Prize, that was given in 2019 to Karen Uhlenbeck for her work on non-abelian gauge theories, which I'll describe shortly. But the modern view of light is the following. You can basically write down everything that gives rise to electromagnetism in one equation that I've denoted in red. The photons are field A mu, and charged particles are a field psi. I won't go through the details. I just want to emphasize the analogies to the what will come later in a non-abelian gauge theory. You see that in the abelian theory, it's quadratic in the photon. So the only coupling that you have is from the coupling of matter fields that comes from this covariant derivative. Okay. To the matter fields. This is the theory of quantum electrodynamics that was awarded in 1965 to Richard Feynman, seen here on top, Shinichiro Tominaga, and Julian Schwinger. And the point is, the basic point is the photons don't interact with themselves. Julian Schwinger, the other physicist, this is a picture of him showing that a physicist only needs pencil and paper to do physics, and of course, coffee or tea. And the reason is because the couplings are very small. The relevant coupling in electromagnetism is 1 over 137 approximately. So you can use pencil and paper. And in particular, on his tombstone, there's just this picture of alpha over 2 pi. So let me explain to you what that is, because it illustrates how you can use just pencil and paper to compute in quantum electrodynamics. So there's a quantity that tells you about the coupling to a magnetic field that's called the anomalous magnetic moment. This was first computed by Schwinger in 1948, and that's the alpha over 2 pi. It's this diagram. I won't describe in detail, but you can see there's one loop there. This is a true quantum correction. And presently, the corrections have been computed to 5 loop orders. So down here to the right, I've indicated what they all look like to two-loop order. And you can see that it's really a quite impressive calculation. It's been carried to many significant digits. Nevertheless, for the particle known as a muon, which is a kind of heavy electron, the difference between experiment and the standard model is 1 part in 10 to the minus 9. And this is now a very big deal in high energy physics because it may be a hint of new physics, such as supersymmetry, that at present we haven't seen in the Large Hadron Collider. Now, the modern theory of nuclei is that you have a nucleus contains neutrons and protons, and these are known as baryons. They interact through the strong interactions, and we now believe that each baryon is composed of 3 quarks and an indefinite number of gluons. The quarks are fermions, the gluons are bosons. They carry a quantum number that's called color. It's nothing like the color of electromagnetism. They're in fact complex 3x3 matrices. And they form a local gauge symmetry. So by the principle I described previously, we have to describe their coupling as a matrix. But now for a matrix, anybody who's done simple matrix algebra knows that even for a 2x2 matrix, that if I take the product of 2 matrices, the order matters. This is what's known as a non-abelian group. And for various reasons, we believe that this is given by a complex, a threefold complex symmetry that's an SU3 gauge symmetry. This is the theory of quantum chromodynamics. Okay, this was first described, in fact, by Chen-Yin Yang and Robert Mills in Brookhaven in 1954, but I'll leave that for those who are interested. The theory now looks exactly like what we had before for electromagnetism. We have some field involving the gluons, capital G, and something involving the quarks, which are now like the fermions. The gluons are more complicated, and the basic point is that besides the coupling of gluons to quarks, we also have the coupling of gluons to one another. This, in fact, leads to a profound difference in the theory. We all know that in quantum electrodynamics, that we can measure a charge at some distance, and it's the charge. Nothing funny goes on. This, in fact, is because the coupling gets smaller at large distances. If you're going to go to very small distances, you find the coupling would grow. In QCD, the gluons, as I said, interact with quarks and one another, and so the coupling becomes smaller at short distances. This is known as the property of asymptotic freedom, and in fact, it's only true for non-abelian gauge theories. This was first understood in the early 70s. This has been verified experimentally. You can, this is what the coefficient is for 3 colors, and F is the number of flavors, which is approximately 3 at low energies in QCD. And you can see that this fall off is very well maintained. So here Q is the momentum, which is opposite to that of the distance. So going to shorter distances means higher momentum. The people who first discovered asymptotic freedom were David Gross and Frank Wilczek, and independently David Politzer, and they were awarded the Nobel Prize in 2004. But it's unlike any other theory because most theories are simple at short distances, at large distances. Here it's simple at short distances, and the question is what happens there. At large distances, the theory is going to become strongly coupled. The answer was first proposed by Ken Wilson, I'm told a few months after the discovery is asymptotic freedom. Ken Wilson was awarded the Nobel Prize in 1982 for his contributions to the renormalization group. But he basically followed his condensed matter colleagues, and he said, well, you just put the quarks on sites, so you have not an infinite, but a finite number of degrees of freedom. And the subtlety is that you have to put the gluons on links in order to respect the gauge symmetry. But clearly, because the coupling is large, we can't use pencil and paper. And so the idea is that, well, we know if we put the theory on a lattice and we make the lattice spacing very small, that we should get the correct theory. So let's put it on a lattice and use a computer. And this is a slide that I stole from Marta Constantinou at Temple University, who compared it to the Gordian knot, that if you can't untie it, you cut it. So if you can't compute it, you simulate it. Now, in the 70s, Wilson said there's no point in even trying to use the lattice because you need much bigger computers. And my colleague Mike Kreutz at Brookhaven said, well, whatever, let me try. And in fact, with the rather primitive computers at the time, he was able to show that one could obtain interesting results, even in the theory with dynamical quarks. And this has spawned the golden age in lattice QCD. This is, in fact, not his typical garb, but this is a picture of Mike at, I believe, a Club Med on vacation. But he's a rather relaxed individual, and he typically wears sandals, but he dresses something like this, albeit without the trident. Now, the basic difference that you can understand between QED, abelian theory, and QCD, a non-abelian theory, is that, as we all know from undergraduate experiments, that the flux line in QED spreads out. So we can pull charges apart and the potential falls off like 1 over the distance. In QCD, instead, you have that 1 over r term at short distances, which you have to have. But then at large distances, instead, you form a flux tube. You get a term that's linear in the separation. So this gives rise to string tension sigma times the distance. And this is a picture from Derek Leinweber showing the flux tube. So this is at one end here. Let's see, that's a quark, and that's an anti-quark, or vice versa. And this is the flux tube formed between. So the question is then how you can tell the presence of quarks and anti-quarks if they're always confined into states with 0 net color. Well, as I said, one thing you could do is to use big computers. This is something that Sayantan has worked with. There's a basic miracle from the 90s. It turned out that you could compute near the continuum limit, that is near a lattice spacing equal to 0, without quarks pretty well. This is a plot of the time, the date versus the logarithm of the computing power. At present, with light quarks, we can compute near the continuum limit, but only for the simplest quantities. And dynamical quantities in particular are much harder. And I'll show you another example that's much harder to compute. Okay, let me skip this. The units in QCD are basically that the proton is small. It's a unit called a Fermi, which is 10 to the minus 15 centimeters. It's quick. It's about 10 to the minus 24 centimeters. And the proton is small. It's very light. And you might think, well, so how can you get something interesting? Well, the point is the mass of the proton is, if you convert into Kelvin, about 5 trillion degrees. And that's what's been to matter for us. And this is naturally why a trillion degrees enters. There's various flavors of quarks. So we'll only concentrate on the 3 lightest, the up, down, and the strange. And this gives rise to particles that are known as pions and kaons, where the lightest pion is about 1/7 the mass of a proton. So this is basically what I'm going to talk about: pions, kaons, and protons. Okay. This is a very dense situation. You could take the whole Earth and put them in a particle collider. Okay. So at low temperature, as I said, we have a confined phase. We have no free quarks and gluons, but just pions and kaons. And because there's a few degrees of freedom, we have a small pressure from a few degrees of freedom. At high temperature, we're going to lose confinement at a temperature Tc and have a transition to a Quark-Gluon plasma. So by asymptotic freedom, the coupling must vanish logarithmically as you go to very high temperature. And in fact, we expect an ideal Quark-Gluon plasma at infinite temperature. in this case, we have a large pressure because we have a large number of degrees of freedom. We have 8 types of gluons, and we have a large number of quarks. So we expect a large increase in pressure in going from a confined phase to a quark-Gluon plasma. And this is what the lattice can tell us, that there is a large increase in the pressure, but no true phase transition. And in fact, the lattice can give us, as you can see, this is a plot of the pressure over T to the 4th versus temperature. So SB here to the right refers to the Stefan-Boltzmann. That's the ideal gas. And the if you look at this pressure over T to the 4th, it's a smoothly varying function. But remember, it's divided by T to the 4th. So in fact, the pressure itself is increasing strongly. You might ask, how can the pressure, the transition temperature be determined so exactly? That's because you can look at the properties of the light quarks and look at the various susceptibilities associated with that. And in fact, the errors now are down to less than 1 MeV. This is relevant to the early universe at about a microsecond after the Big Bang. So let me go on to tell you how to find the quark-gluon plasma in heavy ion collisions. Okay, let me skip this. So the question of why there are heavy ions is that the details of nuclear physics don't really matter, that bigger is better. And so consequently, the field was treated with great skepticism initially, because people are used to looking at proton-proton collisions, where the collisions will be relatively simple with few numbers of particles. And it was thought with a large number of particles that it would be very complicated. And this would be especially true. However, what people forgot is that if you have a large number of particles, average properties can be simple, and especially if they thermalize. So what we want to do is we figure we want a big system, so we'll take the biggest system. Typically, this is either gold or lead. And so the radius will be something like 7 Fermis compared to 1 Fermi for a proton. And there's 2 thermodynamic parameters we can think of. We can think of either temperature or the chemical potential mu, where we have equal numbers of baryons and where you have an excess of baryons over antibaryons. Now, because of technical details, which are known as the sign problem, the lattice today can only do 0 quark chemical potential. And to understand what happens, at very low energies, Coulomb repulsion, they'll come together and then fly away. At higher energies, they'll form one big blob. But what you want to do is go to such high energies that they just go through one another. And the question is, how high? And this was first understood by James Bjorkane in 1983. And basically, this is a plot of the number of particles on the y-axis here versus the rapidity, which is something like this is a central collision. The particles come together and they go through one another. And the point is that as you go up in energy, that you have a larger plateau where the number of particles is approximately constant. And in this region, in this plateau, the number of baryons is very small. So if you want to study a region that's baryon free, you should look at high energy collisions, something on the order of 200 GeV. This idea was first suggested by James Bjorkane in 1983, and I think he's one of the people who, if there ever were a Nobel Prize for this field, would be well deserving of recognition. But the reason why I'm showing these complicated looking graphs is it's just like the flux tube that you saw earlier. You can think of this as the nuclei going through each other is like having 2 test charges being pulled apart and forming a flux tube. And in fact, there are many qualitative models of heavy ion collisions that use this kind of string picture. I'm at Brookhaven, where originally there was an alternating gradient synchrotron here that did a lot of important physics in the 1960s. A tandem for heavy ions was then built in the 70s, and currently what you have is the tandem gives heavy ions. They go to the alternating gradient synchrotron, and then it goes into the relativistic heavy ion collider, this ring that's about 1 kilometer in diameter. Now, you might think that this is clearly an region, the process of very deliberate consideration and the like, but in fact, it was happenstance. Originally, this ring was dug, and it was going to be a proton-proton collider at 200 GeV, and it was canceled in 1983. And it was canceled because they were going to build the superconducting super collider, which itself was canceled a decade later. But Nick Samuels, shown here, who was the director of Brookhaven at the time, based upon suggestions from T.D. Lee, from Larry McLaren, from Gordon Boehm, and others, realized that he could change this from a high energy facility to a nuclear facility. And it was really a very impressive change that I think Nick Samuels deserves a lot of credit for. And if there were a Nobel Prize, I believe he should be awarded it. In contrast, this you can't see at the bottom. This is an animation of what happens at the Large Hadron Collider, where you're colliding properties that are nuclei that are 1,000 times faster, where the energy, instead of being 200 GeV, is 3,000 GeV and even higher. This is a picture of what it looks like there. That's the equations for the weak interactions. And this is an animation of what it's like for when two heavy ions collide. Typically at RIC, you have about 1,000 particles created in a collision. At the LHC, it's several thousand. And you might think because the energies are so much higher that you'd have a much higher multiplicity. But remember, if we're creating a thermal system, that the energy density goes like temperature to the fourth. So a relatively large increase in energy, say a factor of 10 or more, can lead to only a relatively modest increase in temperature. The experiments are large. This is a picture of there were two large experiments at RIC, the Star and Phoenix, and two smaller, Phobos and Brahms. At the LHC, there's one dedicated heavy ion experiment, Elise, and two experiments that were designed for both heavy ions and high energy, Atlas and CMS. And you can see the scale is so much bigger that you can only see one person. And it's really quite impressive that the experiments have been carried through to success so quickly and successfully. Okay, so as I said, why was there skepticism about AA? Why should anything simple arise when you have the production of many particles? And the basic answer is that you can have a statistical system form. And the simplest example of this is the relative abundances of particles, that if you look at, you take a single parameter, the freeze-out temperature, which has here been fixed to be 156 MeV, that it works extremely well down to very rare particles. So there is a small chemical potential, but as I said, the net difference between protons and antiprotons, this is in the central regime, the center of the plateau, is very small. So you can see the difference between protons and antiprotons is negligible. But this abundance goes from pions, which being the lightest particle, of course, the most abundant, down to helium-4 and anti-helium-4. And it's actually theoretically I mean, it's clearly a successful fit to the data, but the question is, why does it work? Why should there be a single freeze-out temperature? You would think that if there were a thermal system, that different particles have different cross sections, they would interact differently as the system froze out, and that doesn't seem what's happening. This must be due to the fact that you're going from a system with a rather large number of degrees of freedom in the high temperature phase to a small number of degrees of freedom in the confined phase. So it's happening very rapidly. And that was contrary to what people had expected when they thought there would be a first order transition or a relatively long-lived state. It appears to last very shortly. When it freezes out very quickly. Okay, so let me go on and explain to you two features of the why we think there's a qualitatively new state of matter. One has to do with the idea that there's elliptic flow, which is the most perfect fluid on Earth. And I'll describe that concept to you. So one thing you can look at is just geometry. So now we have, I'm into the screen is the going down the beam. And so we can clearly have two possibilities. The nuclei could completely overlap and we could have a central collision. But we don't expect that to happen most of the time. Most of the time, they're going to interact. They're going to overlap partially. You have a peripheral collision. And in that case, the number of participants isn't going to be as big as it can be in a central collision, where it can go up. Each nuclei has 200 nucleons, so you can go up to a maximum of 400. But you're going to have some number that could be much smaller. And you're just looking at a hot almond being produced. Now the question is, you can look at the reaction plane. You could look at the difference between, I can't see my mouse directly. Oh, I can't see my mouse. That this between this long direction and this short direction. And this short direction, you're going to see a measure because this is the reaction plane. There's a lot of particles coming out there. Well, that's in position space. We need to transfer that into coordinate space. So as I said, we can look at the spatial anisotropy that tells you the difference between this y-axis, which is long, and the x-axis, which is short for the element. And we can consider what happens if collective effects are present. If they are present, what will happen is things will scatter. And then if they scatter a lot, what we'll do is we'll end up with an approximately spherical surface. That is, in momentum space, it's going to look like this. And so what you can do is you can calculate, instead of the difference, because we can't measure the positions, we can look at the difference in the momenta along the y and the x-axis relative to this reaction plane. This is known as quantity V2. There are higher moments that can be constructed. And you can use ideal hydrodynamics to calculate this. The basic parameter that tells you the deviations from ideality is the ratio of the shear viscosity to the entropy. That's known as eta over S. It's a very effective description. This is a slide from my colleague Bjorn Schenke. So he's looked at the distribution of particles from the ATLAS collaboration, the Large Hadron Collider. So you can measure all of these moments with respect to the reaction plane. Phi is the angle with respect to the reaction plane. And you can go up, in fact, to the 6th moment experimentally. And if you compare this to experiment, the V2 is always the largest, but this hydrodynamic description using a parameter given value for this ratio of the shear viscosity to the entropy works very well up to the 6th moment. Now, this is a function of the particle momentum. It's not going to work up to arbitrarily high momenta because, say, a momenta on the order of 2 JeV is something like 1/10 the size of a proton. And so if you go to very small distances, you don't expect to have collective behavior. This kind of fit also seems to work very well at the Large Hadron Collider. And there it's interesting that the value of the shear viscosity over the entropy that they need is approximately twice as large as given at RIC. So it appears to go up as you go up in temperature. That is, RIC is a lower energy, so it should have a lower temperature relative to the Large Hadron Collider, which is a higher energy with a higher temperature. And that's in fact what you expect from a wide variety of systems, that if you compute in weak coupling, the ratio of the shear viscosity to the entropy is actually inverse to the coupling. That is, the weaker a system, the harder it is to thermalize. A strongly coupled system will thermalize quicker. Now, the value in heavy ion collisions of the shear viscosity is huge. It's about 10,000 times that in pitch tar, but so is the entropy. And if you look at the ratio of the shear viscosity to the entropy versus the critical temperature, so this is the reduced temperature of temperature minus Tc over Tc, so it's a dimensionless variable. In all of these systems, it has a minimum somewhere near the transition temperature. And this value in red here, I'll indicate shortly, but in this case, we believe this is going up because you're going to a weakly coupled asymptotically free quark-Gluon plasma. In this case, it's going up. The confined phase is strongly interacting, but it's becoming dilute, and the density of particles is going away. There was a very interesting connection to a rather abstract branch of physics. As I said, the shear viscosity gets small, it gets large in weak coupling because it's hard to thermalize a weakly coupled system. In 1999, Juan Maldacena, whose picture is here, conjectured that there's a duality between the Gage theory with an infinite number of colors and the most supersymmetry, and string theory on a theory in anti-de Sitter space cross S5. These are both conformal field theories, and he noted that the symmetries are the same and thus conjectured his duality. You can in fact use this to compute at infinite coupling from classical supergravity, and in 2005, Damson, Starnetz, and Kovtun showed that in this ADS-CFT theory that you get a bound of 1/4 pi. And that's close to this value, and in fact, it's close to the value that you get at RIC. And so this picture is a picture of anti-de Sitter space in 2 dimensions from the Dutch artist MFK Escher. And this is a self-portrait of Escher on which I've imposed Juan's picture. Now, there are many open questions. You can get hydrodynamics from the equation of state. You can get that from the lattice, but you need other parameters. For example, it's hard getting the transport coefficients from the lattice. It may be doable eventually, but it's not possible at the present. And it also works really too well. It works up to moment of 2 GeV, which, as I said, is about 1/10 the size of a proton. And it seems to work both for light and heavy quarks. In fact, now it's clear from the LHC that there are differences. Even heavy quarks, such as the charm, appear to flow along with the light quarks. Bottom quarks do not. But the other problem is that it needs to start at a very short time, not 1 Fermi over C, which is the natural scale, but 1/4 Fermi over C. And in fact, as I'll mention at the end, thermalization appears to work not just in heavy ion collisions, but even at systems that are much smaller, and proton nucleus collisions at very high multiplicity. Okay, the other phenomena that we believe is responsible for a qualitatively new state of matter is known as jet quenching, where the quark-Gluon plasma eats jets. Now, hydrodynamics deals with most particles which are concentrated at soft momenta, less than 1 GeV. But in QCD, since it's approximately free at short distances, if you have a very fast particle, it's going to stay a very fast particle. And this gives rise to the observation of jets, of a leading hard particle plus a soft spray. These were first observed at the Large Electron-Proton Collider at CERN. And this is a picture. You can see there's, you just look at it, you see there's two jets. This colors refers to calorimeters, which measure energy deposition. And so this is viewed as you have electron, anti-electron giving a virtual photon producing, excuse me, a QQ bar pair. And then you can also radiate a gluon, and that would give rise to three jet events. And this is long studied in high energy physics. And the idea that, again, was first pointed out by Bjorkane in the early 90s is that if you have a proton-proton collision, you create some jet. This is at very high energies, and they go off, and that's that. But if you create a Quark-Gluon plasma, the jets are going to be affected by transversing the plasma. And this gives rise to the idea of jet quenching. If you have a fast particle, if you're going through, say, pitch tar, it's going to slow down. Its energy is going to dissipate, and it's going to get broader. And this you can see even just by looking directly at the energy deposition. So this is from the Large Hadron Collider. And this is a plot of the direction along the beam. This is the angle relative to the beam. And this is the energy deposition. You can see there's a leading jet at 200 JeV. And then in the opposite direction, you have to have momentum conservation. But there's only 70 JeV. So this other 135 JeV has gone into all of this soft stuff here. And you can quantify that by what's known as a ratio of RAA. You can look at the number of particles in a nucleus-nucleus collision to that in a proton-proton collision. And you can show that that ratio is less than 1. So here, the purple points refer to direct photons. We don't expect photons to scatter because they interact weakly through the electromagnetic coupling, which is 1 over 137. In contrast, the particles should be undergo jet quenching. So you see that ratio is something like 0.2. Now this is from Rick, and at present they can only measure up to 20 JeV. And this looked constant. And so this suggested that perhaps this ADS CFT description would be valid. And that is, you went to high energies, it would just say constant. And the LHC demonstrated that that wasn't true. This is from the Atlas experiment at 5 TeV, so approximately, a much higher energy. And now you can look at jets going up to hundreds of GeV. And you see suppression. And the more central collision in red, you see stronger suppression than the peripheral collisions in blue and green. So qualitatively, it describes things. And in fact, the question is, why is something with a energy of 1 TeV still being suppressed? And that's really something that's very, it's not obvious. It has to do with what exactly you're tagging on and the like. And it's a very active area of both experiment and theory now. There are other questions that you'd like to answer. In the fundamental theory in QCD, quarks and gluons have a different colored charge. So if you could distinguish quark jets from gluon jets, you should see that the quark jet is quenched less than that of the gluon jet, just because the color charge is less for the quarks than that of the gluons. It's very hard picking out these kind of different jets, even in proton-proton collisions. There should also be a qualitative difference between light quarks and heavy quarks due to the scattering processes involved. The color charge is the same, but because of the mass, the scattering is less for heavy quarks. And this is still an unsettled question. Again, it appears that from LHC data that the scattering of heavy quarks does look like that of light quarks, but that of B quarks does look qualitatively different, as you'd expect. And it's surprising that even heavy quarks are behaving in this manner. To understand this better, the energies at RIC are clearly in a transition region, and it would be very interesting studying that by going to higher momenta. And this is what will be done in the next 2 years at the S-Phoenix detector at the RIC. And then there'll be data from CERN that will clearly be ongoing for many, many years. Okay, so let me tell you that the next frontier is moving back down in energy. As I said before, we went up to high energy, so we'd have a baryon-free regime. Now what we want to do is go back down in energy. Now, this is hard for the following reason. What we've done in lattice gauge theory is turn the Lagrangian. Perhaps you want to turn off the speaker in the audience. I hear an echo, which is my fault. Very good. Anyway, and the problem is that when you have non-zero chemical potentials with 3 or more colors, that the weights are complex. Okay, go away. Good. Now, the answer to this is, well, I can always compute in the Hamiltonian form. In the Hamiltonian form, I just have e to the minus energy divided by t plus the chemical potential times the Fermion number. And in fact, this is calculable, at least in principle, using quantum computers. And this, I think, for the young students in the audience, I think this is really a very, very profound area of interest to go into. We probably won't have usable quantum computers for decades, but there are fundamental problems that we need to understand now. And I believe that, in fact, computing the equation of state of nuclear matter is one of the great problems of the 21st century. And I honestly believe that what we all thought of as boring nuclear physics is, in fact, you could calculate it from the equations of QCD using quantum computers. And now I should say that this is somewhat pie in the sky, because for any quantum state, the number of states which contribute is exponentially large. And you need to restrict that somehow. And that's really where a lot of the current effort is going. Okay. But let me show you that you can, in fact, this is kind of a complicated picture. All I want you to take away from this picture is that it's a comparison between experimental results and heavy ion collisions at star. So these had various energies going from 200 down to 20 GeV per nucleon with lattice QCD. And I believe Scienton was involved with these measurements. Now, as I said, the lattice can't compute at non-zero chemical potential directly, but what they can do is extrapolate. They can do a power series expansion, and that's what they've done here. And you see it works remarkably well in comparison with experiment. It's really quite impressive. This is what's being computed is moments with respect to the number density. So what people typically show is a phase diagram of the temperature versus the chemical potential. So what Rick and the LHC have been looking at so far is in this region where it's the phase transition, the chiral transition is just crossover. Now, this may not be true at lower chemical potential, though. As we go down, as we go out in chemical potential, the temperature will decrease. And it's possible that this becomes a first order transition. If that's true, then as pointed out originally by Rajagopal, Stefanov, and Shriyak, there should be a critical endpoint in between. And this is a very interesting, because it would be a true critical endpoint where the correlation lengths diverge. Now, whether you could see that in a nuclei of finite size, but it's something, it is difficult to say. but it's something that you should see at Rick-Fix target, at the FAIR experiment at GSI in Germany, and at the NICA at Russia. Further, as you go out to very low temperature and out in mu, this is relevant to the equation of state of neutron stars as observed by the LIGO experiment that I mentioned at the beginning of the talk. Okay, let me, in the past, I assume I have 5 minutes or so. Let me just tell you some things that I've been working with myself that might be of interest to condensed matter physicists. I consider the usual effect of Lagrangian for an O4 vector. Now, I take O4 because that's the symmetry we think is valid for 2 flavors. But I'm sure those of you who are statistical mechanicians know that, well, at high temperature, we have a symmetric phase where none of the spins line up. And at low temperature, we have a broken phase where the spins line up and we get Goldstone bosons. Well, this is all true if this quarter coupling is positive. But you can also take this coupling goes to 0. And in that case, if both this and this vanish, you then have a tricritical point determined by this cubic coupling. And in that case, as you vary lambda from positive to negative values, you go from a second order to a tricritical point to a first order. And that's exactly analogous what we expect here. This is probably positive lambda, 0 lambda, and then negative lambda. Now, the pions aren't exactly massless, so the second order transitions become a crossover, but we still have a true critical point, which is the tricritical point goes into a critical endpoint. Okay. And there's suggestions that something interesting is going on. You can look at derivatives of the pressure with respect to chemical potential, and you can measure this experimentally in terms of fluctuations. So this is a plot of the fourth order to second order fluctuations. This is going up in energy as you go to the right. So as you go down in energy, you see very interesting non-monotonic behavior. The experimental situation is clearly uncertain yet. There are large error bars at the lowest energy. But it's certainly a very interesting experimental signal. Let me tell you lastly, if I can take a few more minutes, because I just want to have time to mention this. There's other phenomena that are possible. As I said, you can make this quarter coupling change sign. You can also take the coefficient of the terms with 2 spatial derivatives to change sign. And this is very common in condensed matter. In nuclear matter, it's known as pion or kaon condensate. So what happens is you have a rotation between a sigma field and one component of the pion field that rotates as you go along in one spatial dimension. And you can, in fact, show this, find exact solutions in 1+1 dimensions. Now, you might say, well, this is so what? Who knows if this happens? But there's recent work done by a group in Frankfurt. And so I term this the Frankfurt phase diagram. So this is, again, a plot of pressure versus chemical potential. It's in a soluble model in 1+1 dimensions. And it was shown about 13 years ago that chiral spirals appear at low T and high mu. So this is the broken phase. You have a symmetric phase at high T, but at very low T, you get these chiral spirals. It's the average phi is still 0 because as you go along here, you're going to rotate and it's going to vanish. But what's interesting is that you have a large region where this Z, this effective Z, is negative. And that's something that may be possible to see experimentally. This is a plot of a phase diagram. This is now for QCD using an approximate method to calculate where you see a large region in which Z is negative. by Wei-Ji Fu, Jan Pawlowski, and Fabian Rennecke. And we term this a mode spectrum if Z is less than 0 because the minimum is not at 0 momentum. So I'm just going to, given the time, I don't want to bore you too much, but there's one question if they're condensed matter experimentalists who might know. With a mode spectrum, as I said, if Z is negative, the minimum is at non-zero momentum. And it should be possible to see this. This is a plot of various values of the energy for a pion in the mode versus momentum. And if you just plug this into a statistical distribution, well, it is Bose-Einstein statistics, what you're going to see is a peak away from non-zero momentum. Now, the problem is you have to look at a peak at low momentum, and this is difficult for experiment. With Fabian, we also proposed a signal involving two particle correlations where you have a much larger enhancement. This is a ratio of two particle correlations over the square of single particle. I won't go into that. I just want to end by making one point. This is what I want to ask people. In condensed matter, these kind of phases usually arise for O1 or O2 symmetry. With Alexei Tsvelik and Semyon Valgushev, we considered ON for n bigger than 2. Now, in this case, you expect to get Goldstone bosons. And you do. This is a plot of the dispersion relation versus momentum, but it's at non-zero momentum. And if you have that, then what you're going to have is that you're going to have a linear infrared divergence when you integrate about this point. It's like the divergence you get for Goldstone bosons in 2 dimensions, except it's even more severe because it's in 1 dimension. So it's a linear infrared divergence. We could solve this model at large n and show that a mass gap to the Goldstone bosons was generated dynamically, which we turned a type of pion liquid. And what is being blocked out here, let me see if I can just move this without messing things up, is there an example in condensed matter? This must be a general phenomenon. And it'd be interesting to know if there are such examples. Well, given the time, let me just conclude with, there are many things that I didn't have time to cover. I didn't have time to cover the chiral magnetic effect with recent results from the STAR experiment, which unfortunately did not see evidence for a chiral magnetic effect, although various theorists disagree. Let me just conclude by saying, in fact, one of the most astonishing things is before people would say, well, you never thermalize in heavy ion collisions. If you look at, say, proton nucleus collisions, usually you get about 5 particles per unit of rapidity. But in 1 in a million events, you get a much higher multiplicity with 50 to 100. And the question then is, what does that look like? And in fact, it looks very much like the Quark-Gluon plasma. You can apply hydrodynamics, and it appears to give a very reasonable description of the data. So we're now seeing, it's not a question of things thermalize, but they seem to thermalize in places where we really wouldn't have expected it. As long as you have a large number of particles produced, it appears we can use a thermal description. Now, of course, that doesn't prove there is, but it's very suggestive. So with that, I'd like to conclude that this is a picture of the Great Wave of Kanagawa by Hokusai, and there's just this wealth of experimental data. And we're here in theory trying to understand things, and there's just so much. But I think it's a field that's of great interest, and in particular, going down in energy, I think is something that will be of great interest for the decades to come. And with that, I thank you.
Thanks, Rob, for this very comprehensive review. And it's time for questions if someone wants to ask.
Hello, can you hear me?
Yes.
Okay, so at like 1-2 slides back, you mentioned about a symmetry O1. Yeah,
Yeah.
O1, the first line. So I'm sort of confused. So when you talk about O1, like U1, I understand it's a phase transformation. What does O1 do?
Yeah,
Because
you're right. I apologize. I was sloppy. I really mean Z2, where you just have a plus or minus, like a Ising model.
okay. So
Yeah,
okay,
yeah,
okay.
yeah. I was imprecise. I should have said Z2. But for
Okay.
the point I was making, for either a single component or a two component field, uh, if you have Z negative, everything goes into the chiral spiral and there's nothing left over. You need ON with n bigger than 2 in order to get a chiral spiral and to have Goldstone bosons. And I don't know an example of that in condensed matter. And neither does my colleague Alexei Tsvelik, who is a condensed matter theorist. But there must be something, and it'd be very interesting to see if this type of quantum pion liquid is arises.
Okay. And one more question. You mentioned that
Yeah,
one place that lattice cannot do calculations for non-zero mu.
right. Except by
Can you please?
extrapolating a power series. Yeah.
Okay. Can you please explain why? Sorry, I don't know.
Yeah, I wish I knew a simple explanation, but it's not, because, for example, at for two colors, the question is, you want to evaluate the fermion determinant. It's determinant of D slash plus I mu gamma naught. If you don't have chemical potentials, you can show that the eigenvalues line up. So you have complex conjugate eigenvalues, the product is real. If the chemical potential in Euclidean spacetime is minus I mu, and so typically they don't line up. That's basically the reason. You have lambda minus I mu and lambda conjugate minus I mu, and their product is not real. That's a little hand waving, because it turns out for two colors you have an extended symmetry known as Pauli-Guercet symmetry that tells you that this determinant of D slash minus I mu gamma naught is still real, but that's not obvious. So I guess the short answer to your question would be, without chemical potential, it's D slash. Those eigenvalues come in complex conjugate pairs. With chemical potential, it's D slash minus I mu gamma naught, and they don't pair up. Why it's an I is something you have to sit down and work out. We'll see if I
Okay,
have
okay. Thank you, thank you.
Oh, no. I have a simple explanation. The reason it has to be I mu is because if it was just mu gamma naught, it'd look like the time-like component of a vector potential, and you could gauge it away. So the I tells you can't gauge it away if you coupled it to a U1 gauge theory.
Okay, okay. I'll give over.
Yeah, it's easier to write on the board, which I don't want to try doing that because I'll mess something up. But it's not completely obvious at all.
Sorry.
Sayantan, do you have a better explanation? Yeah. Okay.
Sorry, one has to just speak through the mic, so that's why.
Yeah.
No, it is fine. Yeah. Like,
it's not a simple thing. It's not.
The
obvious.
number density operator is Hermitian. That's why the Dirac operator is anti-Hermitian. That's why the mu comes as with an I factor. Yeah.
Yeah.
So in the Dirac operator, mu comes with an I, and then that's why there is a problem. Yeah.
Sir, did you say that this mu chemical potential can be gauged away by the gauge transformation? Is that you said?
No, if it were real. What I said, it's minus I mu. But in fact, the when you treat non-zero chemical potential, the gauge fields that enter are no longer SU3 gauge fields, but SL3 gauge fields. The gauge fields that enter become complex. So no, you can't gauge the mu away, but the gauge fields you have to consider become more elements of the special linear group instead of the special unitary group. The gauge fields become complex because the mu that enters is complex.
Okay. Okay.
Hi, sir. So when we are going from continuum to lattice, so while discretizing this, so we are losing some symmetries like translation symmetry, and so is there any consequence of that?
Yeah, that's a large part of why it's difficult. It's going from the lattice to the continuum limit. There are many things you have to check. One thing I didn't have time to go into is that for some bizarre reason, it turns out to be relatively simple to put gluons, which have this local gauge invariance, on the lattice. You put them on the links, you take the continuum limit, you can check. I mean, one thing you could certainly check is rotational symmetry. Excuse me. If you're on a lattice, you'll form multiplets according to some discrete spatial group, discrete rotational group. And in the continuum, they should form multiplets of spin and parity and the like. But with quarks, they have this, I didn't have time to go into it, they have this global symmetry of called chiral symmetry. It's just a global symmetry. You'd think it would be easy to put on the lattice. And in fact, it turns out to be extremely difficult. And that's really the reason why it's hard doing quarks in the continuum limit, is that this chiral symmetry, this global symmetry, is very hard to discretize and ensure that you get all of the right symmetry behavior that you'd expect. So yes, the short answer to your question is absolutely, you have to make sure you're getting that the continuum limit recovers all the symmetries you know that are there that you have to pick up in the continuum limit. And for some bizarre reason, it's just much harder with fermions than it is for gluons. It's really quite unexpected.
Also, this continuum limit, like computationally, we can't put a to 0. So is there any minimum value we put this lattice spacing, like some less, what is the number we are putting for this continuum limit?
Yeah, I believe certain people can certainly, Cyanton can answer better than I. They can certainly go to tenths of a Fermi, I believe something like 0.05 Fermi. But typically what people do is they quote several values of A. They look at some quantity like a mass, and then they plot that versus A. And hopefully the slope is not large and the extrapolation to the continuum limit is valid. But it's something that you always have to worry about. It's not obvious that for all quantities. And as I said before, there are many quantities that you can compute masses, you can compute the equation of state, you can compute moments, but for example, you can't compute transport coefficients. As I showed you, this ratio of the shear viscosity eta over the entropy S is essential to compare to experiment. The entropy you can get from the lattice, the shear viscosity, there's no believable result at the present time. So there are many quantities of experimental interest that are just very hard to get. Typically, they have to do with, besides the sign problem, the things that are not in equilibrium, but near equilibrium to real-time processes. And that should be addressable with quantum computers in the decades to come.
Oh, thank you. Last question, we use this square lattice. So can we take another lattice like triangle lattice or hexagonal lattice? Is there any difference that will make? Like, in many
people have
sides,
investigated. Yeah, no. It's a good question, particularly if if you're worried about restoring symmetries. People have considered, for example, random lattices in the hopes of making it easier to go to the continuum limit. The problem with that is these are large-scale simulations that involve many people, and it's just easier taking a well-defined set of parameters so that you can use the same configurations to compute different quantities. So in principle, it shouldn't matter, but in practice, it's not something that's been explored widely, just for practical reasons. I guess I'd have to say it's not clear you really gain that much. That people can do the extrapolation to the continuum limit, and for most quantities they can compute reliably. You don't see a strong dependence upon the lattice spacing with modern techniques. I should also mention the advances in the field are due not only to the increase in computing power, but also to algorithmic development. And that's been a large part of it as well.
Okay. Thank you, sir.
For the audience who are joined by Zoom, do you have any questions? Please, you can unmute and ask.
Sayantan, can I ask one?
Yeah, please go ahead.
Hi, Rob. So I had a question on the freeze-out plot that you showed with proton and helium-4 abundances and all that.
Yeah.
So I was just wondering, is that something that is like how much of QCD dynamics goes into determining that? Or is it more of a Boltzmann suppression kind of thing that gives you those yields?
Right. You mean?
It was way back.
Yeah.
This one here, yeah.
Right? No, that's what's so amazing. This is a fit that you give any undergraduate Boltzmann law, or not Boltzmann, well, it probably is Boltzmann. I doubt it depends upon whether it's Bose-Einstein or Fermi-Dirac, but don't quote me. But you give them the standard, statistical distribution function with one parameter, this freeze out, and it describes all of this. I think it's the most bizarre thing in the world. There's no dynamic. In answer to your question, there's no dynamics going in.
I see.
It's one parameter and the masses.
Is there some reason to expect that dynamics should not affect this?
I think there's every reason to expect that the dynamics would affect it.
I see.
I just, because look, if you have a system that thermalizes and it's expanding, then all of these different particles have different cross sections. And they're going to interact differently, and you'd expect them to freeze out at different temperatures, depending upon their cross sections. Look, helium-4, helium-3, the deuteron is very weakly bound. Why is it working? It's over what, 9 orders of magnitude?
Is it that they're all color singlets, and so is it that their like interactions are very weak and therefore they don't matter? Is that?
I mean, the usual explanation given is the freeze out happens because you have go from a large number of degrees of freedom to a small number of degrees of freedom. It happens very quickly. Okay. And yes, then in the low temperature phase, it just blasts apart and it becomes dilute very quickly. That certainly must be what's going on. But it's still astonishing.
So the fact that it happens very quickly, maybe you're saying, is what? explains this. Okay.
But it'd be nice to quantify that. It'd also be nice to see, all the particles that aren't here. The problem is all of these, they're affected by feed down from higher resonances and the like.
Okay.
But it's really, it's one of the things why in the last slide I showed theory being overwhelmed with experiment, because like to 0th order, everything agrees with your naive expectation, and I can give words that it freezes out quickly. But if you look into the details, it's just, and you think, well, how would I do better? And it's like, how are you going to do better than this?
Okay.
I hope I've given you. If you're surprised, you absolutely should be. Does that answer your question?
Yes. Yeah.
It's really, I don't get it.
Okay. Yeah, I had one more question on the jet quenching, a very naive question. So if you have 2 jets, so which are back to back maybe, but why don't both jets quench? Is that the dominant, probabilities for both to quench, but there are some with only one quenched? Is that
right? It depends where they are. I mean, you could have one that's like right on the edge and that goes out.
Ah, I see.
And then the other has to transverse a long way.
Okay.
So but you're absolutely right. If you have a jet and it's right in the middle, then you'd expect each of them to quench equally. Yeah. So they're to give them they're geometric effects that you have to take into account as to where the original jets originate. Absolutely, you're right.
Okay. All right.
And that's why most of this is statistical. It's hard to do on an event by event basis because you're not going to know where in the Quark-Gluon plasma it started.
Okay, thank you.
Are there any more questions for the Zoom audience? Okay, I don't see any. So Rob, I had a question regarding your last topic on the quantum pion liquids. You mentioned about this Bose-Einstein kind of distribution for them. But surprisingly, it is happening at a finite momentum, right? It's not the zero momentum state that is condensing. It's the finite momentum state. So what is the symmetry that causes this? Like, what is causing?
It's not really condensing. It's the most probable.
Okay.
I mean, here, what's interesting about a mote is that the faster you run, the easier it gets. That's the way Larry McLaren once described it to me, right?
Okay.
You're used to, the lowest energy particle is at zero momentum. You just stay at rest. Here, it's not really condensing per se, unless this touches, has zero energy. As for a Bose-Stone boat.
Okay.
So it's really more trivial. It's not condensing. It's the lightest thing.
And
you
expect this to be visible beyond the first order transition when you increase the density, or where do you expect to see these signatures?
Well, I assume most of the experiments are now in this region and they haven't reached this region.
Okay. So it's beyond the first order one.
It's above. It's at higher temperatures. Yes.
Okay.
Yeah.
So in the quark-ionic phase, if it happens, it will happen.
Yeah.
Okay.
Yeah.
Thanks a lot, Rob, for this fascinating talk. You spent almost 1.5 hours with us. Thanks for the time.
Very good.
Also, it was a privilege for us that you kindly agreed to give a talk as a part of our 60th year celebration. And thank you very much. And we hope to see you in person here at some time.
Let me thank you again for the invitation and to wish the Institute congratulations on their Diamond Jubilee. And to say, lastly, I would love to come visit sometime. And I look forward to it.
Thank you.
Very good.
See you then.
Take care.